Yes, sir.
Okay, fine. So I should share. Right. So recording has been started. So I should share my screen first. Okay. Now can you see the white screen?
Yes, sir.
Okay. So, so this is the second and last lecture on relation. So I have discussed that what is the partial order relation and what is a poset, but I recall this again. So partial order relation. So what was the partial order relation? That's mean if X is a set and R is a relation on X, then R is said to be a partial order relation if R is, that is, R satisfies these three properties, that is, R is reflexive, R is antisymmetric, and R is transitive. So if a relation R on a set X satisfies these three properties, then we say that the relation is a partial order relation, and the pair, this XR, that's mean the set X with the partial order relation R is called a poset. Okay, and from now onward, when we say that this that is a relation is a poset, then this R is denoted by this symbol, that is that less than equal to symbol. Okay, so instead of R we will write this, so that's mean this we will write as X, and this is my relation. Okay, so that's mean by this relation it does not mean that it is a usual less than or equal to. Okay, so that's mean we define this here, actually we define this in our way, right? So it is not the usual less than or equal. Okay, so it is just a symbol, it is just a symbol. And why we are writing in this way? Because it gives a partial order. That's mean we can give a new order. For an example, in a natural number we know that 1, then less than 2, less than 3, less than 4, right? So this is a natural ordering. Okay, but we can give a new order. For an example, we can give say 1 less than 3 less than 2. This way we can also rearrange that, right? So therefore we can give a new order there. Similarly, we can give a new partial order as well. Okay, so just take this as a symbol. So that does not mean that it is a less than or equal. Okay, now there is a concept called dual poset. Dual poset. So let X, this is my relation, this be a poset. Okay, now then, now see, this is my this symbol. Okay, now if we define a new relation, then the relation this one. Okay, so you can call it as a less than equal to if you want. You can call it is a greater than equal to, but just remember that you can call it because you have to read something, right? So that is not wrong. But when you are saying that it is less than equal to, that does not mean that that usual less than equal to. Okay, so that's all. So then this relation this on X defined by, so A this getter equal to B if and only if B less than equal to A. So that's when we know this symbol, right? We know this is the given. And this is the new symbol, right? Now, if this symbol is given, then we can define a new relation by this symbol in this way. So A greater equal to B if and only B less than equal to A. Okay, so this is given and this is new. Now it is easy to check that this is also a partial order relation, right? Also a partial order relation. You can check that. This is very simple. Okay. Now the pair this is called the dual poset of. Okay. So that was the given and we find this is the new. So this new one, this pair is called the dual poset of the given pair this. Okay, fine. So that's mean from now onwards, we know if we have a relation this, then we know this relation as well, right? And this is called the dual of that. Okay. Now, from the poset, we can give a covering relation as well. What is a covering relation? So if you have any question, if you have any doubt, you should ask. So this, I know this concept is not difficult, but if it may arise some confusion. So if you have any kind of confusion, you may ask. Okay. So what is a covering relation? So let X this less than equal to symbol, that is a relation, be a poset. Okay. Now define.
Uh, Here in the above definition, A and B are the elements of X.
Right. So
And
yeah.
and there the meaning of greater than or equal to is it the one we already know or
No,
I
you
didn't
don't
get.
know. You don't know. Because see, what is a greater equal to means it is not the usual greater equal to. So we have to define that. But we will define in this way. That's when if B is less than equal to A, then we say that A is greater equal to B in this way.
I didn't get. Sir. Means what's the meaning of that greater than or equal to here now?
This one, that is B is less than equal to A.
Okay, okay,
For an example, suppose you are less than equal to means A divides B.
okay,
Then,
okay. Means it
then,
is
huh,
means we can define by ourselves what it means by less than or equal to.
exactly.
With that we can define greater than or equal to.
Exactly. That's mean if A less than equal to B means A divides B, then A greater equal to B means A is divisible by B.
Okay, okay. No, okay. Thanks.
Okay.
So, sir, like every element in X need not be related to each other, right?
No.
Okay.
Yeah, we will see that one as well. So now if we have a less than equal to, that is that if you have a poset, so this is a poset, then we can define a relation, a new relation. This one, so only less than on X by this way. So A less than B means if and only if A less than equal to B and A not equal to B. Okay, in this way you can define this. So suppose you know less than equal to, that you know have a poset. Now you can define a new poset, not a poset. You can define a new relation this by this way. Okay, so A is less than or equal to B, but A not equal to B. In this way, you can define this. Okay, now you can check that this is a relation. So for all AB in X. Okay, now in this way, we will say that now here B is said to cover A if A is less than B and there is no element C in X such that A less than C less than B. Okay, so that's mean if you have two elements A and B and suppose A less than B and there is no other elements, obviously A less than B means A is not equal to B and A less than equal to B. Okay, and there is no element C between them, then we say that B is a cover of A or B cover A. You just can say that. So we will see now one example so that it will be clear to you.
Sir, here equal to is the normal equal to, right?
Right. This is so equal to means it is always equal, means
Okay.
normal equal. Otherwise, how can we say that equal? Okay, so this is the usual one that how to say that this is the usual one. So actually, what is our aim? So in a natural number, in a real number, we have a ordering. It is a natural ordering, right? Now what we can generalize that. So that's mean actually it is not a generalization. Those relations come from here only. Okay, so we can define. So now we will see one example. Then it will be totally clear to you.
Sir, A less than B is a normal less than.
No. Now I will give one example so that there will be no other confusion. Okay. Now say this X is the set of all positive divisors of say 30. Okay, so this is my set X and relation R or not R, I will say less than equal to that A less than equal to B means we define this A divides B. We can just use as a symbol. Just A divides B. Okay, so in this way we will define that. So this is our relation. So we define in this way. Okay. Now tell me what is your set X? What is your set X here? Since it is a all positive divisors of 30. So that's when the set X is 1, 2, 3, right? This is not 4 will not be here, 5, 6, then 10, then 15, then 30. Okay. Now you can check that this is reflexive because if you take any element from X, then X divides itself, right? So therefore X is reflexive. So reflexive as A divides A for all A belongs to X. And it also antisymmetric. Why it is antisymmetric? Because A divides B and B divides A. And this is only possible if that imply A equal to B. So that's mean A less than equal to B and B less than equal to A. This is our relation, less than equal to, imply A equal to B. And third one is transitive. Why it is transitive? Because A divides B and B divides C, imply A divides C. So that is, you can say that if A is related to B and B is related to C, then A is related to C. So X is a poset. Okay. Now tell me, is there any relation between 2 and 3? Can we say that here? Yes or no?
No, sir.
No. So in here, so that's when if you choose any two arbitrary pair, we cannot compare them. So we cannot compare. Okay. So that's mean we know that 2 here less than equal to 6. So this is right.
What you mean by we cannot compare?
Huh? Sorry.
What you mean when you say we cannot compare? What it is mean?
Okay. So that's mean right. So that's mean A is 2 is not related to 3 and 3 is not related to A. So or you can say that 2 is not related to 3. So this is the meaning of compare, not compare. Okay. And also 3 is not related to
Sir.
huh. So that's mean between 2 and 3 there is no relation. So that's mean we cannot compare because 2 is not related to 3, 3 is not related to 2. That's all. But here 2 is related to 6, right? Because 2 divides 6. Okay. Also here, since 2 less than equal to 6 and 2 is not equal to 6, we can say that 2 strictly less than 6 as well. Right? That was the definition of covering. Sorry, this defined this one. If and only if this is less than equal to B and A not equal to B. So therefore we can say that 2 is strictly less than 6. Now can you tell me 6 is a cover of 2 or not? Yes or no?
Yes.
Yes, sir.
Yes. So here 6 is a cover of A, or you can say that 6 covers A. Fine.
But
Now
sir,
what?
so exists,
So 3 is a number that exists between them.
and sir 3 divides 6.
Oh no, sorry sir.
But 2
No.
does not divide
2 is
6.
not less than
The
equal to
2
3.
does
Yeah.
not divide 3, right?
Yes, sir. Understood.
Okay. Now what about 3 and 30? Is it true? 3 less than equal to 30? Yes or
No.
not? True?
Yes.
Yes, sir.
Yes. That's mean 3 less than 30 as well. Now can we say that 30 is a cover of 3?
No.
No,
No.
sir.
No,
Because
no,
Six.
sir.
Six. We have
because
6.
we have
Yes,
6
6, 15 also.
and we have 15 also. Okay. So we have a covering actually diagram. So there is a covering diagram. That's mean we have a all of this path. So how we can go? Now it is called a covering diagram. So that's when this is a diagram to say that which is covered of which element. So here you can see that you have first is 30, then we have 3 actually 15, 10, 6, then we have 5, 3, 2, and this is 1. And how they are related? So 1 goes with this. Now 5 goes with 15 and 10. Now 3 goes to this and 6. 2 goes to 6 and 10, and then this. So this is the diagram. So from this diagram, it is clear that 6 is a cover of 2, 10 is a cover of 2, 5 is a cover of, 10 is a cover of 5, and 5 is a cover of 1, but 15 is not a cover of 1, because between 1 and 15 you can go via this way and this way. So you have two elements between 1 and 15, 3 and 5. So this is called a covering diagram.
Sir.
Yeah.
Sir, what does it mean when we say 2 is less than 6? Not
So
the
this
equal.
is the, yeah. So this way you have defined, right? So what is our definition? You can check here. So in this here, we have defined in this way. This is our example. See. So we will say that A less than equal to B if and only if A divides B. So since 2 divides 6, so therefore we will say that 2 less than equal to 6. And this is our set.
Okay, it means that other way around is not true. Only A divides B is true, so we can say 2 is less than B.
Right.
If
Since they are
B
not,
divides A, then we can say A less than equal to B.
if B divides A,
Yes,
then
if both way is true.
both they will be equal, right? It is the
Yes,
definition of
sir.
coset.
Yes. Yes.
Since 2 divides 6 and 2 is not equal to 6, therefore we can say that 2 strictly less than. So that was the definition of this. Covering. Oh, what is covering? So this is the definition. This. Okay. Now why we are saying that it is a partial ordering? Note that suppose now you have a usual order. Suppose you have a usual order on this set X equal to 1, 2, 3, 5, 6, 10, 15, 30. So this is an usual order, right? But here we are giving a new types of order. Okay. So this is not an order. This is called a partial order because we cannot compare any two arbitrary elements, but we can compare some of them. So we can order partially. Right, so we have a diagram, so we can cover, we can order partially. So therefore, this kind of relation is called a partial order relation. Okay, and also we will define an order relation as well. So there is that term is different. That order relation. So order relation means you can uh, compare any two elements. Okay. So is that clear to everyone? Okay, fine. Now in a poset, we can talk about the least element and talk about the greatest element. For an example, look at this diagram. Can you tell me, if you look at this, what is the least element of this set? This set?
One.
Right. So 1 is the least element. And what is the greatest element of this set?
30.
Right. So actually, you don't know the definition, still you can say, because it is the definition is already clear. Now suppose this is your set. So that's mean our X is this one and we are removing this 1 and 30. 1 and 30. We are removing these two. And our set is this and we are giving the same order relation this. Now can you tell me what is the least element of this set?
2, 3, 5 all are least.
Okay, what is the greatest element?
15, 10, and 6.
Okay, no, so that is not correct. Now in that case, you do not have any least element. Okay, and you do not have any greatest element. So we will see the definition. What is the definition of least element? Okay, so least element and minimal element both are different. So in that case, there will be no least element, there will be no greatest element. Okay, and there is a concept called minimal element and maximal element. Now here 2, 3, 5 they are minimal elements and 6, 10, 15 they are maximal elements. But this set does not have any least element. Okay, so we now define what is the definition of list element. So let this be a poset and say S, say subset of X. Okay, we can say we can take one just subset of X. Then the list element. So why we are saying the list element? Because actually by the definition, it is clear that the list element, if exists, that will be unique. So therefore we are using here the. Okay. So then the list element of S is an element. A belongs to S such that A less than equal to X for all X belongs to S. Remember that here it is for all. So that's mean if you want to talk about a list element, then you should compare that element with every element. Okay. So therefore, from this definition, you can see that this poset does not have any list element. Is that clear? Because you cannot say that 2 is a list element, because 15 you cannot compare 15 with 2. That's mean 2 is not less than equal to 15. So therefore you cannot say that 2 is a list element. Similarly, you cannot say that 3 is a list element, because 10 is not less than equal to 3 is not less than equal to 10. Similarly, 5 is not a list element, because 5 is not less than equal to 6. Is that clear? That list element?
Sir,
Ah,
sir, if instead of 15 we have another number which is divisible by 2, and the other three numbers are arranged in that way, then can we say 2 is the list element because it is divisible by all of
I did not get your question. It was not audible. Can you repeat again?
Sir, is it fine now? Sir, my
It
voice
is
is fine now.
no, I cannot. Yeah, just try again. Try again.
Okay, sir, I will write.
Okay, okay. Yeah, better to write. Okay, you just write. So in similar notion, we can write that what is a greatest element. So similarly, so let X bigger equal to this one. Oh, sorry, not this one. So this be a poset and a subset of X. Then the greatest element of S is an element, say B belongs to S such that X is less than equal to B for all X belongs to S. So here again we have for all, and this is the. And why we are writing the? So by the definition, it is clear that list element, if exist, is unique. And similarly, we can say the greatest element. So in a partial order set, that least element or greatest element may not exist, but if they exist, then they should be unique. So therefore, we have writing here da. Okay. What is yes?
Sir,
What is the question?
sir, if instead of 6, 10, and 15 we have 30, 60, and 90, then what will be the case?
Okay. Right. So what you are giving example instead of? So you can give me the set. What is the set? Hello. Hello. I am not audible.
Yes, sir, you are audible.
Tell me. So what is the set?
Sir, instead of 15, 10, and 6, we have 30, 60, and 90.
Okay, so that's when you are saying that 2, 5, 2, 3, 5 and 30,
30,
60,
60, 90.
90.
Yes, sir.
Now still it does not have any any least element, right? Because 2 is not comparable with 3.
Oh, okay, sir. Yes.
See, that's it. A is a least element. A is the least element if A less than or equal to X for all. Right? So in that case also you cannot compare 2 and 3.
Okay, sir.
Okay. So that's when to be a least element, it should be comparable with all of the other elements.
Sir, what is S in this definition?
S is can be any subset of X.
Okay, sir.
Sir, if
Even
it,
you can take S as a X as well. That is fine.
So, sir, whether the least element will exist or not depend on what we choose as S.
Right. So I am taking that least element of S, right? You can say that least element of X as well. That is up to you. For an
Okay.
example, if you choose that set, say 2, 6, 10. Suppose this is your S. Then you have a least element. Say that is 2. Then 2 is the least element, but there is no greatest element.
Okay, sir, got it.
Okay.
sir, in this definition, sir, you have written A less than X for all X belongs to S. So, sir, if A is least element, sir, A less than equal to A is also necessary condition or no?
A is always less than equal to A, right? Because it is a poset.
Oh, okay. Okay.
Now, I already told you what is a maximal element and minimal element, but I write as a definition. So what is a maximal element now? Maximal element. Remember that it is not maximum. Okay, it is maximal. Or we can define and minimal element. Now let X, this relation be a poset and S subset of X, then an element A belongs to S is said to be a minimal element. Why we are right here A? Because that minimal element may not be unique. Okay, is a minimal element of S if X less than A for no element X belongs to S. So that's mean there is no element which is less than A. So that's all. For an example, if you look at this, see this is 2, there is no element less than 2. So therefore 2 is a minimal element. Similarly, 3 is a minimal element. Similarly, 5 is a minimal element.
Sir, there is no element less than 3.
Sorry?
There is no element less than 3. It
Huh.
means what does it mean? We have to define
That's
2 less
mean,
than equal to
yeah,
3
in
and 2
general,
is
that's
equal to
mean there is no element in this set which divides 3. So in this set, so that was our set. There is no element in this set which divides 3. So that's mean there is no element which is less than 3. Okay.
Sir, so if we have a number like 7 in the set above, so that will be both the maximal and the minimal element.
Here you cannot have 7, right? Because we have taken our main X was it is a divisible by it is
Oh,
a
yes.
all the positive divisors of 30. So you cannot
Okay.
have 7 here in this example.
Okay.
If you want to include 7, then you have to define a new relation there. For an example, instead of you can choose natural number and
Sir,
so
if
for an example,
least
you can
element exists, then it will be minimal also. Of
exactly right. Good observation. So if you can take X equal to this and this as A divides B, it is also fine. Here also you can find that the order relation. So now one observation that the student told that if list element exists, then it is a maximal element as well. Okay, so that's mean if you have a list element of a set, then it has only one minimal element. It is a minimal element. So that's mean if you have the list element, then it has only one minimal element. Okay. Now similarly, you can define maximal element. Maximal element. So B belongs to S is maximal if there is no X in S such that P less than X. Okay, now we can see another example. Say my X is all proper subset of this power set of 1, 2, 3. Okay, all the proper subset of this set. Okay, then tell me what is a maximal element, greatest element? Tell me what is the minimal element, what is the greatest element, what is the least element? X is all the proper subset of this, and the relation is, since it is a set, say A less than equal to B, if and only if A is subset of B. Okay, so this is our relation. Now tell me, what is the maximal element? Or what is a maximal element? Or what is maximal elements?
1, 2, 2, 3, and 1, 3.
Okay, so maximal elements are 1, 2, 2, 3, 1, 3. What is the what is minimal elements?
Empty set.
Singleton set. Sorry.
Yeah, empty set. And greatest?
It doesn't exist.
It does not exist. And least?
Empty set.
Again empty set. See, it is simple. So this is the just difference between the least element and greatest element. And sorry, greatest difference between greatest and maximal and least and minimal. Okay, so this is simple. Now in similar notion, you can define also upper bound, lower bound as well. Upper bound and least upper bound. Okay, now we can define upper bound. Now let X this be a poset. Okay, and say A, B, two element of X. It is a poset and we choose two element. Okay. Now an element C belongs to X is said to be an upper bound of the pair AB if A less than equal to C and B less than equal to C. Okay, or you can say that C is a upper bound of the set AB. You can say that one as well. Okay, so here we need that definition upper bound of a pair. So that is the reason we are defining upper bound of a pair. You can define upper bound of a set as well in the similar notion. Okay, so you can define upper bound of a set as well in a similar notion. So that's when you can compare all the elements of this set from with the element C. And what is the definition of least upper bound? Now again from the definition it is from the name it is clear. It will be upper bound and it is the least. So U is said to be the least upper bound of the pair AB if first of all U is an upper bound of the pair A and B, and secondly it is the least one. That's when if there is any or if there is another upper bound C of the pair A and B, then U less than equal to C. Okay, so if U is an upper bound and among all the upper bound, if U is the least one, then we say that U is the least upper bound of the pair this. Okay. Again, why we are using it is the, because if upper bound exists, then it should be unique. Now see one example. So let X equal to say power set of some set. Okay. And A less than equal to B means actually A subset of B. In this way, you are defining the partial ordering. It is easy to check that it is a partial order. Now, can you tell me what is the least upper bound of the pair A and B? Can you tell me what is that?
A union B.
Right. It is just A union B, because A union B is an upper bound of A and B both, right? And this is the least one. So you cannot have any upper bound which is lies between A and A union B. Now in similar notion, you can define the lower bound as well. So let this be a poset. Okay, and say AB belongs to again X. Now an element say L belongs to X is said to be lower bound of the pair AB if L less than equal to A and L less than equal to B. And L is said to be, or not L, we can write a different one. So an element B belongs to X is said to be the greatest lower bound if the two properties satisfied. So first of all, lower bound of the pair A and B if first of all B is a lower bound of the pair A and B, and the second one is B is the least one. So if there is any another lower bound L of the pair AB, then B is the greatest one. So L less than equal to V. Okay. So similarly, here in this example, what will be the greatest upper bound? Sorry, greatest lower bound? A and B, that will be, it is easy to see that it is just A intersection. Good. So if we take another example, say my poset is natural number and this where A less than B means actually A divides B. Now what is my least upper bound of AB? Can you tell me what is the least upper bound of AB and what is the greatest lower bound of AB?
LCM and HCF.
LCM and HCF.
Right. It is LCM of AB and it is the GCD of AB. Okay.
Sir,
Ah.
an example where you were like where you wrote that x is equal to all the proper subset of power set of 1, 2, 3, where we found the maximal, minimal, greatest, and least element.
Ah.
Sir, what is between all the proper subset of power set of 1, 2, 3? Means first we have to make the power set, and then we have to make a subset of those.
So what is your set? You are saying that X is a power set of 1, 2, 3 only.
No, sir. All the proper subset of power set this.
Huh.
So
So
you
that's
put
mean this minus 1, 2, 3. Right?
1, 2, 3. Acha, that means it does not. I cannot understand it. What does the proper subset mean?
No. Proper subset. Oh, you did not get what is that? Okay. So that's mean this set. This means all the proper subsets of this. So okay. I think I had something in a mind and I just wrote a wrong thing. I think. Just a minute.
I think it should be like the power set of this only.
Got it. All the proper subset of sorry.
1, 2, 3. I think.
Okay. Good point. Better to write it is the collection of all proper subset of 1, 2, 3. This one. Right? So this means actually power sets of 1, 2, 3.
Yes, sir.
And then set minus this set 1, 2, 3. That singleton set we have to delete this one. Yeah, good point. I had this one in my mind and I just wrote a wrong thing. Okay. This notation is also clear, right?
Yes, sir.
Okay. Good. Thank you for the correction.
Sir, if we take hello.
Yes.
Sir, if we take set of 4 elements 2, 3, 30, 36.
Right.
And our relation is divide 1.
Okay. We are seeing a new one. So your set is 2,
3,
3,
30, 36.
Okay.
And our relation is defined as A divides B. Yeah.
Right.
Then what will be the lowest lower upper bound of 2, 3?
Oh, that does not exist.
Yeah. Okay.
Okay. So that does not exist. So LUB.
But upper bounds, but upper bounds do exist, right?
Right. This does not exist and oh, sorry, not upper bound, lower bound. Greatest lower bound does not exist, but least upper bound of 2, 3. Here that is 30. Oh, just a minute.
So why is it 30 and not 36?
Why
Okay,
it is
okay,
30?
just
It
a
should
minute,
also not exist.
just a minute. What was the, yeah, that is good observation actually. So what was our definition?
Sir, the definition does not include a relation, I think. No?
So this is an upper bound, that is a least one as well. I think just a minute.
So in the definition of the lower bound and upper bound, the less than equal to is the symbol of this like coset now or normal less than.
No, I am now little bit confused. So what you are saying?
The less than or equal to
Sir,
symbol.
sir, there are multiple upper bounds like 30 and 36
Right,
both are
30
upper
and
bounds,
36 both are upper bound.
but there is no
Then
least element of that set of upper bounds. Therefore, least upper bound should not exist.
yeah, but what was my definition? Least upper bound. So that's mean, is there any mistake in that definition? So if there is another, right. So that second property does not, right. The second property does not satisfy here. Right. Thank you. Right. So what is that? So we cannot say that 36 is a least upper or 30 is a we cannot say that 36 is not the least upper bound or 30 is the least upper bound. So it also does not exist. Does not exist. Why? Because 30 and 36 both are upper bounds. Of the pair 2 and 3, but we cannot say that 30 is less than equal to 36 or 36 is less than equal to 30. So they are not comparable. So therefore, that upper bound also does not exist. Good one. Right. The second property does not satisfy. Fine. See, that is the property. So if there is another upper bound C of the pair this, then U should be less than equal to C. U to be a upper bound, least upper bound. So here, if your U is 30, right? Then C is another. So this 30 is another upper bound, right? But 30 is not less than equal to 36. So therefore, 30 cannot be the least upper bound. So it has two upper bounds and they are not comparable. So therefore, least upper bound does not exist. Good. So I also got confused on that. Okay, fine. So is it fine to everyone? Yes. Okay. So now we have a new definition called lattice. So what is a lattice? So a poset X, this less than equal to, is called a lattice. If every pair of elements of X has the least upper bound and the greatest lower bound. Okay. So for an example, if you take natural number with this relation, then is this a lattice? Yes or no?
Yes, sir.
Yes, sir.
Is a lattice. And what about that set? If you take 2, 3, 30, 36, and with the same one, so A less than equal to B, A divides B, then this is not a lattice. Right? We have seen that if you take the pair 2, 3, it does not have any least upper bound and it does not have any greatest lower bound as well. Okay?
Sir, finite set can't be lattice. Uh,
Sorry?
Is it right or not?
Finite set?
Cannot be a lattice.
Why?
Because it will have a maximal element. And if we take a pair with a maximal element, then there will be no upper bound.
No, that does not make sense.
Sir,
You can just take a simple one, say 1, 2, 3, 4, and if say less than equal to means usual one.
Sir, so in this case, if we have a pair like 1, 2, then the greatest lower bound of that pair does not exist, right?
Why?
It
1.
should be 1, right?
It is 1.
Okay.
Okay, it is just 1. If you take 1, 2, and if you take that greatest upper bound, that is just 2. Sorry, lowest upper bound. Yeah, least upper bound, that is 2. That is fine. It is lattice.
Okay,
yeah,
so lowest upper bound and lowest upper bound and greatest lower bound can belong to that set we are taking, right?
Okay. So sometimes these easy things also get some confusion, right? For an example, I was getting confused here. Because when you talk about that least upper bound, greatest lower bound, then maximal element, minimal element, least and greatest, then all of things sometimes get confused. But it is fine. But sometimes it gets some confusion. Okay. So I hope this portion is clear. So now there is another relation, that is the last type of relation. This is called the order relation. Now that order relation, so there is a difference between partial order relation and order relation. In the partial order relation, if you take any two arbitrary pair, so they may not be comparable. That's when you may not compare them. But in order relation means if you choose any arbitrary pair, you can compare them. That is called the order relation. And for an example, when we see that natural number, real number, they have some natural ordering, which we know. Even we can define a different order, that is fine, but they have a natural ordering, right? For an example, in natural number 1 less than 2 less than 3 in that way, or in integer 1 less than 2 less than 3, and similarly -1 less than 1, -1 less than 0, -2 less than -1 in that way. So what is a order relation? So a relation R on a set X is said to be an order relation if it satisfies these three properties. So first one, for every pair x, y in X, for which x not equal to y, so that's been different pair, we have either x related to y or y related to x. So that's mean you always compare any two distinct, sorry, not any two pair means any two pair of distinct element. And it is non, that mean for no element x, this holds. And third number is transitive. So that's mean for any or for every x, y, z in x, x related to y and y related to z imply x related to z. So for a order relation, so n order relation is usually denoted by this symbol. So not usual. So we will use that less than symbol, okay? But it is not the usual ordering. For an example, say my x equal to say natural number, okay? And we define x less than y if and only if. So either x square is less than y square or x square equal to y square and x less than y. Oh, not less than y. X is less than y. So that is the usual one. That is the reason I am writing here in terms of language this. Now can you tell me what will be the ordering of natural number? Or sorry, not natural number. It is not interesting. Z. Now can you tell me what is the least element of this set? Yes.
So 0.
0.
And then
-1.
yeah, -1, then -2. Oh, sorry. 1.
1.
Then it is -2, then 2 in this way. So this is the ordering. Right? And similarly, you can, yeah, sorry. You were not audible.
I got actually I was confused with the second point when I see that x is less than y. Actually, I did not want to negative.
Fine. Okay. Now suppose you have an order relation. From this on, you can go to the poset as well, right? How to define a poset? So order relation to partial order relation. So order relation to partial order relation. You can go to a order relation to a partial order relation. How you can go there? For an example, yes.
What you written like this? 0 less than -1 less than 1. What is this?
So this is our usual. This is our new ordering here. We are defining in this way that order. So x less than y, if and only if in this way we are either x square is less than y square, or if both are same, x square equal to y square, then we are taking x is less than y. In that way, we are defining the relation between x and y. So that's when if you compare 0 and -1, you can see that x square is not equal to y square, right? So therefore here x square is less than y square. So therefore x is 0 is less than -1. And if you look at -1 and 1, their square are same. So by the second property, -1 less than 1. And similarly by the first property, 1 less than -2.
And what this whole thing is? Why we are writing this? What we are trying to do?
So we have a set Z and we are giving a new ordering there. That's all. Okay, one Z you already know one order. For an example, 1, 2, 3, 4, and the previous one before 1 it is 0, before that it is -1 in that way, right? Now we are giving a new order here in Z. So in this way we can define a new order and we prove that this is a order relation.
So what we will write Z is equal to like 0, -1, 1, -2, 2, like this.
Right. So that's when in a set Z we are giving a new order. That's all. Maybe I did not get your question. Are you trying to say something else?
Means I was saying like that the new set Z will be like 0, -1, then 1, then -2, then 2, like this.
Right. So what we are actually just saying that we are giving a new order here. For an example, how should I say this one? Right. So suppose you have a set 0, 1, or just a finite set. Now this finite set has a natural ordering. You know that 0 less than 1 less than 2. This is a natural ordering, right? And this ordering satisfies that all this ordering property. But you can define a new order relation here as well. You can just define the 0 less than 2 less than 1. Now if you define in that way, if you define in that way, still you can prove that that is an order relation. And if you have a set and if you can give a order, any order, then that set will be called a ordered set. So I can write a definition as well. Ordered set.
Sir.
So
here the less than sign means the relation between 0 and 1.
Right. So here 0 less than -1 means 0 is related to -1.
Yes.
So here we are giving us a new ordering. That's all. So what we are trying to say that, see, right. So why we are, you can ask that why we are trying to give a new ordering. So that will be useful when you want to prove that natural number the integer z, the set of integer that is z is countable. That's when you can count them. So you can count them in this way. So to count z, you have to start somewhere, right? So you can count in this way. So for an example, you can count 0, -1, 1, -2, 2, -3, 3. In this way, you can count. So therefore, you can say that it is a countable set. So there you are giving a new ordering, and that is the ordering. Similarly, when you prove that your rational number is countable, then also you can give there a new ordering there. And we will see all of this ordering. Okay, so what is an ordered set? So let this is be a order relation on a set X So then X is said to be X with this pair is said to be an ordered set. Okay. Since I do not have much time, I just want to define in, just give one definition and then I will stop. So that definition is immediate predecessor and immediate successor. So let X be a set and this be an order relation on X. Okay. Now if A less than B, then we can define this interval, that is open interval AB. So that's mean it is all the elements X such that A less than X. Okay. Now if this set is empty, then we say that A is the immediate predecessor of B and B is the immediate successor of A. So for an example, if you take natural number, say with usual order. Okay, natural number n with usual order. Now can you tell me what is now this open interval, this 1 2? That is just empty set, right? That is just empty set. So therefore here 2 is called a immediate successor of 1 and 1 is called a immediate predecessor of 2. Okay. Now suppose you have R with usual ordering. Okay. Now can you tell me what is a immediate successor of 1?
Not defined.
Yeah, it does not exist. And similarly, if you take rational number Q with the usual order, then can we talk about that immediate successor of 1?
No, sir.
No, still we cannot say. Right? But if we take natural number or integer, then we can say that 2 is the immediate successor. Okay. So fine. So today we stop here from the, in the next lecture. So I could not finish the relation part. Okay. So in the next lecture also, I will start with relation and then I will finish that and then I will start the set.
So have you shared the tube 3?
Sorry, the solution.
No, tube 3, tutorial 3.
Yeah. I have already sent you the tutorial 3. See, I always send you the tutorial, all the tutorials in the MS Team as well as in the Imparters. So if you have access to the Imparters, then you can always find that.